Hello everyone and welcome to the chapter summary for Edexcel's A2 Statistics Chapter 3. So, as usual, starting off with the objectives for the chapter. Our first is to understand the normal distribution and its characteristics. The second is to find percentage points and calculate values on a standard normal curve. Our third is to find unknown means and standard deviations for a normal distribution. Our fourth is to approximate a binomial distribution using a normal distribution. And finally, to model and carry out hypothesis tests to solve real-life problems in context. And then to finish off, we have an exam question. So, first of all, what is the normal distribution? Well, the normal distribution is a continuous distribution, and it looks something like this. And this type of curve is called a bell curve, and it's centered around a mean, which we call mu. And this is a continuous distribution because values can take any value in a given range. Now, one key fact about the normal distribution is that the area underneath the curve is always equal to 1. And that is true of any continuous probability distribution. The notation associated with normal distributions, so if we have the continuous random variable x, we can say this is normally distributed with an n, and its parameters are mu, the mean, and also the variance, sigma squared. Now, some other key points about the normal distribution is that, first of all, it's symmetrical about the mean. And so this means that the mean is equal to the median is equal to the mode. And also we need to know that there are points of inflection on this curve, so here and here. So where the graph turns from being convex, so the gradient is increasing, to concave, where the gradient is decreasing. And the same for the opposite side, where the graph is concave, and it then turns to convex. And these points of inflection are at mu minus sigma and mu plus sigma. We also need to know some key statistics to do with where the data lies. So we need to know that approximately 68% of the data lies within one standard deviation of the mean. 95% of the data lies between 2 standard deviations of the mean, and finally 99.7% lies between 3 standard deviations of the mean. And just a little note here, although a normal random variable can take any value, in reality observations a long way from the mean have probabilities close to 0, as you can see as the curve starts to level off on both sides. We need to be able to find percentage points and calculate values on a standard normal curve. And this can be done using your calculator. So on the class quiz, you'd first go to menu, and then press 7 for distributions. Then press 2 for normal CD. And that will allow you to find probabilities from a normal distribution. So you will have a menu that shows a lower value that you have to input, an upper value that you also have to input, the standard deviation, and the mean. So for example, if we have the random variable x, which is modeled with the normal distribution with mean 30 and standard deviation 0.4 squared, and we're trying to find the probability that 31 is less than x is less than 32, then our lower value will be the 31, the upper value will be a 32, and our sigma will be 0.4, and our mu would be 30. And putting that into our calculator, we get our answer is equal to 0.006209. And looking at this visually on a normal curve, so here our mean is 30, our value 31 will be somewhere here, and our value for 32 somewhere here. And then what we can see is that this probability here, the area under this part of the curve is equal to 0.006. Now, if we're trying to find probabilities such as probability that x is less than 29, if we look at what we're trying to find on the normal curve, so our upper bound will be 29, and we need to choose a very low value for our lower bound. So for example, minus 1000 will do, and that just ensures that our value for the probability is to a sufficient degree of accuracy. If, for example, we were to make that 20, then 20 might be here, for example, and we're forgetting about all of this probability after 20. But because the probabilities get really close to 0 really fast as we move away from 30, choosing a number like minus 1000 will ensure that our probability is very accurate. We also need to be able to use the inverse normal function on your calculator. And what this inverse normal function does is that if we have a distribution here, the normal distribution looks like this. Let's say with mean 25. What the inverse normal does, to find it on your calculator, you just go to menu, press 7 for distributions, and then number 3 for inverse normal. What this allows you to do is input an area, your value of sigma, the standard deviation, and the mean, mu. So let's say that the standard deviation here is 1. If we put in an area of 0.4, what that will do is find the value such that the area to the left of that value is equal to 0.4. So if we press equals on our calculator, we get that this value here is 24.74. So you input the probability to the left of a value you want to find, the standard deviation and the mean, and it gives you the value of the distribution so that the probability of x being less than the value is equal to your given probability. We also need to be able to find unknown means and standard deviations for a normal distribution. And to do this, we need to use the standard normal distribution. And this has mean 0 and standard deviation 1. And we often write this with the variable z. So that if we have a variable x with normal distribution mu sigma squared, we can code this into using z is equal to x minus mu over sigma. What this essentially does is the x minus mu part on top shifts the entire distribution for x back by mu so that it is centered on 0, and by dividing by sigma, this essentially scales this pushes the distribution for x inwards. This squishes the distribution for x so that its standard deviation sigma is equal to 1. So if, for example, we have the random variable x, which can be modeled using a normal distribution with mean mu and standard deviation sigma, and we're given that the probability that x is greater than some value a is equal to, let's say, 0.3, and the probability that x is less than some value b is equal to 0.2, then we could be asked to find the value of mu and sigma. And to do this, we need to use our equation to standardize the normal distribution in x. So that is z is equal to x minus mu over sigma. So first of all, we can look at the standard normal distribution. So z with mean 0 and standard deviation 1. That looks something like this. With mean 0, such that the probability of z being greater than c is equal to 0.3, which corresponds to this probability statement here. So this area here is equal to 0.3. And also we're looking for a value d such that the probability that x is less than d is equal to 0.2. Which corresponds to this equation here. Once we have these values of c and d, they will give us our z for these equations here, and the x values are given by a and b. So for our first equation here, we have our z value is equal to c, our x value is equal to a, and we have minus mu over sigma, and here we have our d value is equal to b minus mu over sigma. So let's call these equations 3 and 4. We can solve these simultaneously to gain solutions for mu and sigma. And our next objective is to be able to approximate a binomial distribution using a normal distribution. And the reason why we'd want to do this is because for a binomial distribution, as x values become large, calculating the probabilities becomes very difficult. So instead, we can use a normal distribution to approximate a binomial distribution. And there are some conditions that have to be met in order for the normal distribution to be a good approximation to the binomial distribution. The first is that n must be large. And the second is that p must be close to 0.5. So under these conditions, then we can say that x, which is binomially distributed with number of trials n and the probability of success p, can be approximated with the normal distribution with mean mu and standard deviation sigma, and the value of the mean we can approximate as np. This is the mean number of successes we're expecting, and we can estimate the variance using np1 minus p. Now when we do this, we have to apply something called continuity corrections. Now these continuity corrections account for the fact that the binomial distribution is discrete and the normal distribution is continuous. So for example, if these bars show the probability for a binomial distribution, okay, it looks something like this. Okay, where this is 1, this is 2, this is 3, this is 4, and this is 5. And then we have a normal curve which looks something like this, which I'll draw in red. If for the binomial distribution we're trying to find the probability that x is greater than or equal to 4, then that includes everything that I'm shading in blue. But if we're finding the probability that x is greater than or equal to 4 for the normal distribution, then actually what we're finding is just this bit here after 4. So we're missing out this entire section here from 3.5 to 4. And so what we do is we apply a continuity correction. So instead of looking at the probability that x is greater than or equal to 4, instead, for the normal approximation, we're looking for the probability that x is greater than or equal to 3.5. Now if instead we're looking for the probability that x is less than 3, then on our binomial distribution, we're looking at the shaded area in blue again here. So the bars at 1 and 2. But if we're looking at the normal distribution, we also include from 3 here. We also include this section there. So you can see that we also include this little bit here from 2.5 to 3, which we don't want to include. So instead, for our normal approximation, we'll be doing x is less than or equal to 2.5. And of course, because the probabilities at a single point on the normal distribution is equal to 0, we can also write these as the probability that x is strictly greater than 3.5, and here the probability that x is strictly less than 2.5. And this is the convention for writing probabilities using the normal distribution. And finally, we'll be looking at hypothesis testing with the normal distribution. And we'll be carrying out the hypothesis test with the observed sample mean. So this is just the mean of all observed data in the sample. And that will be given to us in the question. And then we have to determine whether or not the mean that is given for the normal distribution is correct or not. And so if we have the random variable x being modeled by a normal distribution with mean, mu, and standard deviation sigma, then the sample mean, which we write as x bar, is going to be normally distributed with the same mean mu but its variance will be divided by n, where n is the sample size. And we divide by n here, because what we are saying is the greater the sample size, so the greater the value of n, the less the means of the sample will deviate from the mean, mu. Here, dividing by n essentially has the effect of squishing the normal distribution inwards. As the means of the samples are more likely to be closer to mu, the mean of the entire population. Now, the null hypothesis here is going to be that mu is equal to the value given in the question. Let's call that A. And the alternative hypothesis will be that mu is either greater than A, or mu is less than A, or mu is not equal to A, in which case we have a two-tailed test. And here, to find the critical value, we can either do this from the tables, from the formula booklet, or we can use the inverse normal function on your calculator. So for example, if we had a significance level of 5%, then we need to find the value here, such that the probability of x being less than that value, let's call it C, is equal to 0.05. And that will tell you the critical value. So finally, to wrap up, we have an exam question from June 2018. The lifetime L hours of a battery has a normal distribution with mean 18 hours and standard deviation 4 hours. Alice's calculator requires 4 batteries and will stop working when any one battery reaches the end of its lifetime. And part A says find the probability that a randomly selected battery will last for longer than 16 hours. So here we're simply being asked to find the probability that L is greater than 16. And so using your calculator, so menu, distribution, and then we're going to normal CD. Our lower will be 16, our upper will be a large value, so something like 1000, and our standard deviation will be 4, and the mean 18. And that gives us our probability of 0.6915 to 4 decimal places. At the start of her exams, Alice put 4 new batteries into her calculator. She has used her calculator for 16 hours, but has another 4 hours of exams to sit. And part B asks us to find the probability that her calculator will not stop working for Alice's remaining exams. So here we can find the probability that an individual battery will last the extra 4 hours, and then raise that to the power of 4 to find the probability that all 4 batteries will not stop working for the remainder of Alice's exams. And we have to be careful here, because we know that she has used the calculator for 16 hours. So we're trying to find the probability that L is greater than 20, given that L has already lasted 16 hours, so L is greater than 16. And using our conditional probability formula from chapter 2, we have this is equal to the probability of L being greater than 20 and L being greater than 16, or just L being greater than 20, because if it's greater than 20, then it will be greater than 16 too, over the probability that L is greater than 16. So, finding the probability that L is greater than 20, using your calculator again, just swapping out the lower value from 16 to 20, gives us 0.3085 to 4 decimal places. So this gives us 0.3085 over 0.6915, and this is equal to 0.4461 to 4 decimal places. Now all we need to do is raise this to the power of 4 to find the probability that all 4 batteries will not stop working for the 20 hours, which gives us 0.0396 to 4 decimal places. Now, for part C, Alice only has 2 new batteries, so after the first 16 hours of her exams, although her calculator is still working, she randomly selects 2 of the batteries from the calculator and replaces these with the 2 new batteries. Show that the probability that her calculator will not stop working for the remainder of her exams is 0.199 to 3 significant figures. So, for these new batteries, we need to find the probability that these will last more than 4 hours. So the probability that L is greater than 4. So putting that into your calculator from the distribution menu, normal CD, lower 4 on upper, let's say 1000, with sigma equal to 4 and mu equal to 18. This gives us 0.99976, so on, so on, so on. And we have 2 of these batteries and 2 of the other batteries which are the same as in part B. So using the same probability in part B. And remembering from before, the probability that L is greater than 20, given that L is greater than 16, was equal to 0.44621. So, because we have 2 new batteries and 2 of the old batteries, we need to square both of these values here, multiply them together. So, we have that the probability is equal to 0.99976 squared times 0.44621 squared, which is equal to 0.1990 to 4 decimal places. And finally, for part D, after exams, Alice believed that the lifetime of the batteries was more than 18 hours. She took a random sample of 20 of these batteries and found that their mean lifetime was 19.2 hours. Stating your hypotheses clearly and using a 5% level of significance, test Alice's belief. So first of all, our null hypothesis is going to be that mu stays the same, is equal to 18. And our alternative hypothesis is going to be that mu is greater than 18. And we're using the sample means distribution. So we have the same mean, but the variance is going to be divided by the sample size, which is 20. Now we need to find our critical value, which will look on the curve like the point here. Let's call it C, where the probability that x is greater than this value of C is equal to 0.05, the significance level, so that this area here is equal to 0.05. And we can do this using the inverse normal function on your calculator, but the inverse normal only finds areas to the left of a value, and the area to the left of this value C is going to be 1 minus the 0.05, which gives us 0.95. So, going to menu, then distribution, then inverse normal on your calculator. I'm putting in the area of 0.95 with the mu equal to 18, and this time the sigma equal to the square root of 4 squared over 20, making sure you input that carefully. That should give you 0.8944 for the value of sigma. And pressing equals, we get that our value of C is equal to 19.471. And we can see that Alice's value, 19.2, is less than the critical value. So we fail to reject H0, and we can conclude that there is insufficient evidence at the 5% level to suggest that the mean lifetime of the batteries is greater than 18 hours. And that is the end of the chapter summary for chapter 3. I hope you enjoyed and you find these videos useful, and I hope to see you for the mechanics chapter summaries. Thank you for watching.